Hello. Let's begin. Is everyone excited? There we go. So, let me just do some... Here's some stuff from 201. Now let's look at some 341 stuff. Nice. All right. So let's do some announcements, I guess. All right, because that's what I usually do at the beginning of each class. Seems like something to do. Project 4 is going to be on hash tables. I'm going to go over hash tables on Tuesday. I might actually do a hash table lecture so I was thinking we've lost, at this point we've lost 2 lectures. I could do a hash table lecture like tomorrow, maybe, just to make up a lecture. That way you'll have at least some idea of what hash tables are before you go into them. I haven't received the preview copy of the project from the course chair, so I'm not sure 100% what kind of hash table it's going to be, but we can talk a little bit about hash tables today as well. I think we'll probably have time. We'll probably have time to discuss hash tables today, perhaps, maybe. What else? Oh yes, the exam 1. So, I'm not going to make the TA grade that, I'm going to grade it. Okay, so I'm going to grade it over the weekend. That's it. That's it for that. So, yeah, we might try to recover like a hash table lecture. One of the if we actually do try to recover a lecture, then I'll do something about hash tables. If we don't, then whatever. Project 4 should be, hopefully Project 4 is about Project 3 level difficulty, right? I mean, there's only so much you can do with hash tables in terms of difficulty, so... But I mean, I can't really make any promises because I haven't seen it. Okay, that's unless, of course, maybe if we projects. Let's see here. If we secretly check, nope, nothing there right now. Okay. Anyway, I think that's it for announcements. Yeah, so let's do Fibonacci heaps now, because I've been wanting to do them for a while, and, you know, I haven't. So the first thing I want to do is I want to finish up with the binomial heap stuff. So you remember how I wrote the binomial heap code, and I couldn't quite get it working within one class period, and that was always really disappointing and, oh, you know, very sad. So I just want to show you that it was theoretically, like, this is working code, and I'll upload it to the GitHub right here, this one line. So when we were doing remove minimums, I wasn't setting a the node that we were deleting to null pointer. And if you don't do that, then it still tries to merge with it. So let me just show you the code working, and then hopefully it doesn't break, because I shouldn't have changed anything. So if you remember, we can insert something like 10, insert 20. And the only other reason why you might want to talk about binomial heaps again is because let's insert 15, insert 31. And now remember what happens if we insert 31. And I mean, you might be like, why is he going back to binomial heaps again? The answer is that Fibonacci heaps and binomial heaps are very similar. There's a few... Basically, the way to think about it is that a Fibonacci heap is like a lazy binomial heap. So let's... Or you could call a binomial heap a very strict Fibonacci heap if you want to do something like that. So remember what happens here. These two B0s get merged into a B1, and then the two B1s are going to get merged into a B2. So we're going to end up with 10 being the root. 15 is going to be a child. It'll have 31 as a child. 20 is going to be another child of 10. There we go. So we have 10. Its children are 20 and 15. And the child of 15 is 31. All right, so now what? Let's insert 3. Let's insert 32. I want to insert things that are not the minimum, so insert 15, insert 71. So now we have a full set of things, right? We have a B0, we have a B1. I don't know why there's this extra space there, but whatever. We have a B1, and we have a B2. Now, if we delete the minimum, it's going to delete this 10. And so what's going to happen? It's going to try to merge this 20 with the 71. So we're going to end up with a B1 who has a 20 with a child of 71. And then it's going to merge these two 15s, right? It's going to merge the two 15s, and they're very similar, right? And it doesn't matter which one is going to merge. I think what's going to end up happening is that this B1 will become a child of this B1, but again, it doesn't really matter. So remember the command that I used was just remove. And so here's what you see. You see that here it merged the two B0s into a B1, and it merged the two B1s into a B2. And so now if we remove again, let's see what happens. So it's going to give us a B0, which is 32, and then it's going to merge the two B1s. So we're going to end up with a B0 and a B2, like that, right? It took this B0 and put it here, and then it merged this one with this one, right? Because it removed 15, so we have this B1 left, B1, and we have this B1 left, and that's what you do, right? So now we can insert like 17, insert 13, insert 21, insert 52, 51, insert. Now I have to insert some bigger things like 43, insert 42, I guess, insert 67, insert 80, whatever. Ooh, command not recognized. I always like to put nice little error messages in. So, is this good enough? This is good enough. And you see why I was doing this, right? I was putting in a bunch of nodes so that I can delete the minimum, and the minimum will be this one. If the minimum was this one and we deleted it, right, it would just put this into the B0 column and nothing else would happen. So it'd be kind of a boring thing. It's always more exciting in a binomial heap when you delete the biggest BK for whatever K is, right? So, so here we're going to remove it, and so this B0 is just going to go in here, so that's going to be that. This one's going to get merged with this, so we're going to end up with a B2. This B2 is going to get merged with this B2, and we're going to get a B3. So it allows us, so the advantage of a binomial heap is that it basically allows us to merge in log n time. So when you merge two heaps, there's basically, like you have in leftist heaps and skew heaps, there's a merge operation. So leftist heaps and skew heaps have a merge operation that operates in log n time, and so does the binomial heap. It's just like a different way. It's like a completely different algorithm to make a heap, but it makes the merge operation go in log n time. So here we go. Let's remove. And so remember, we're going to end up with a B0, I think a B2, and a B3 in the end. So, yeah, so we ended up with a 21, we ended up with this, and finally we ended up with this. So as you can see now, as it turns out, it was just that one line of code. This is actually kind of a hint for your project. You don't actually have to do this line of code, but you do have to... I wrote this comment. Don't forget to forget. And that comment is probably more applicable to your project in set priority function. You will need to remember to forget, most likely. And basically what you'll have to do is you'll have to merge two heaps. I think you'll probably have to do that in merge heaps as well. You'll have to remember to set something to null pointer in order to forget all of the stuff on one side. If you don't, then you might end up with double freeze, which some people have had. It's a common problem basically. If you ever need to forget something, you'll have to set your heap to null pointer. But of course that doesn't make any sense because that's not actually part of the code here. But anyway, so this actually looks pretty good to me. I mean, I haven't tested it out with things like, 500,000 elements or anything like that, so I don't technically know that it works, but it looks like it works, right? It's doing the right operations. I must admit, I do kind of like how it prints out this stuff. I like my little tabbing stuff. It does make, even for command line output, it does look kind of okay. So, I'm going to quit this. No seg fault either. I think this program probably has some memory leaks because I don't think I'm not sure that I actually coded the destructor properly or anything like that. If you remember, I think all I did was I deleted proot. Oh, but then I think I made the destructor inside of here. So hopefully, theoretically, it should do okay. So now that I've reminded us, now everybody, we know what binomial heaps are. We understand them extraordinarily well, right? And we see that I didn't completely fail. I actually wrote nearly working code. I just kind of couldn't seem to get it working last class. As it turns out, it's hard to live code things. So now let's talk about Fibonacci heaps. So I want to start with the Fibonacci heap visualization, and then we'll go to the Fibonacci heap lecture notes that I've sent out. So okay, so let's begin. So let me just start with a whole bunch of examples of how to insert and stuff, and you'll see that this is almost the same as a binomial heap, kind of, right? So here's the way that it works to insert. Basically, when you insert, you're going to have a vector, okay? And I've put the animation speed up to like absolute mega maximum. So let's insert a bunch of numbers: 22, 13, 15, 71, 285, 12, right? And let's insert 3 finally. Okay, and so you see that what it's doing here is this is literally just a vector, right? This is just a vector or a linked list or something, right? So there's nothing terribly special about this. There's actually an internal representation. Let's see how this is like a doubly linked list is the way they're doing it. You can just do it as a vector. There's no reason to do this as a doubly linked list over a vector or over anything else really. Okay, so there's nothing special here. The question is just, what do you do when you want to remove the smallest element? Now I'm going to take the animation speed all the way down well, maybe I'll just leave it here, and I'll remove the smallest, and then I'm going to pause. So it removes the smallest element because it knows where the smallest element is. Remember what it does is it's going to always track where the smallest element is. Okay, and now here is where we go into like binomial heap time, right? Because what would you call all of these nodes right now, right? You would call them all B0s, right? But then you notice that instead of adding those B zeros immediately, we just added them to a list, right? So now, let's see. So basically, here's the next, what they're calling the next element. And so next element, you see, is going to get put into the 0 slot because it's a B0. And then I guess it might go to 22. Okay, there we go. So now it's going to go to 22. So now we see that we have two B0s. So we're going to have to merge them. So now we're going to merge them and create a B1. So we'll stick that in the 1 slot. There we go. So now we're going to go to the next element. That's going to be a B0 again. Cool. And I know that I'm calling them B0s. In Fibonacci language, they call them rank 0, rank 1, rank 2. And the rank is equal to the number of children that each node has. So here this is a rank 1 thing because the root node of this tree has 1 child. Here this is rank 0. So basically, I mean, I don't care if you call them B0s or rank 0s or whatever. The point is pretty clear. Right, so the number of children of the root node is equal to the rank. So this is rank 1, this is rank 0, and all of them are rank 0s right now. And then what you do is you basically say, okay, here's another rank 0. I'll combine it to a rank 1. And then you say, well, binomial heap rules say, I cannot have 2 rank 1 subtrees, or I can't have 2 B1s. So make a B2. Cool, done. All right. Now we have another B0. Put in the 0 slot. Now we have another B0. Merge it. B1. And I know I'm calling them B1s. I'm abusing the notation. Abuse of notation. That is a common thing. So here, now we have a B0, we have a B1, and we have a B2. And then this 5 element is going to do our full merge. And there we go, we have a two B1s, and now we're going to get another B2, and then finally, we're going to make a B3. The end. The end. Right? And you would say, okay, that seems fine. I can kind of go with that. But you ask, why did we do it this way? The answer is because now insert, let's think about the order of, the type of thing that insert has to do. Like, let's just think about what does insert have to do, right? Right? The first thing that insert has to do is it has to go to the position of the minimum and compare. So, whoops. So if it's the new minimum, mark it. And if it's not, don't mark it, right? Don't set the new minimum as min. Or don't set the new value, I guess I could call it. Okay, so that's basically what you do. And so, and we already, we know that we remember where the old minimum was. So this is an O of 1 operation, right? And then the second thing you do is you do a vector dot pushback of the new value, right? Really what it is it's node of new value. But either way, how much is this, right? What does this cost? This is an O of 1 operation as well, right? So basically the point here is that this does fewer operations in terms of the insertion. So overall, insert is always O of 1, and this isn't even amortized. This is not amortized, which means it's not averaged out over a bunch of operations. This is a true O of 1 operation, which is kind of impressive, right? It's an O of 1 operation on an object that is like a heap, right? So insert is O of 1. And then you ask, basically, you know, what is remove? And you see what remove does. What does remove do? Remove basically takes the minimum out, just like a binomial tree, a binomial heap, and then what it's going to do is it's going to merge the min node children with the current heap, right? And so the only thing that we have to argue here, and they have a special way of arguing it, the argument has to be that merge is, merge is not actually O of log n. Technically, merge is O of n, which is terrible, right? Absolutely the worst possible. Right? It's not really possible to, well, I guess you shouldn't say that. Like O of e to the n or O of n factorial would be worse, but this is not great. But the argument is going to be that the amortized time is log n. And so what does that mean? Basically, all that means is that if what we do, if we sum over, basically amortized time is equal to the, basically it's equal to the time per operation. It's really the sum over the operations divided by the number of operations, right? So if we can add up the time per operation and then divide by the number of operations, the argument is that it's actually log n. And so that's why you want to do something like that. And so the thing is that it's kind of like with a vector. So the vector implementation is also amortized constant time. But the reason why it's amortized constant time is because basically whenever you insert into a vector, so like I don't know if I've talked about this before, but if you insert into a like std vector, it does one of two things. One, it could just puts the element on the end of an array. Done. That's O of 1. Or two, if the number of elements, right, is going to be bigger than the size of the internal array, then what it has to do is it has to copy it allocates an array of 2 times the size of the internal array. And then what it does is it has to copy everything from the previous array, and then it deletes the previous array. So that is how the internal STL vector works. And so you might ask yourself, if it works like this, why isn't an O of n operation? Why don't people count this as an O of n operation? And the answer is, well, it's actually basically what you would say is that occasionally it's an O of n operation. And so basically the way that it works is that, let's say that the internal size is like 5, right? So if the internal size is 5, well, let's make it, there we go. So that means that what we can do is we can insert 1 element, we can insert 2 elements, we can insert 3 elements, we can insert 4 elements, we can insert 5 elements. Only when we go to the inserting of 6 elements do we have to do the copy operation and all of that. So basically, the cost here is equal to 1 plus 1 plus 1 plus 1 plus 1 plus 5 for the copy, right, when we insert the 6th element. But the point is that if we take the total cost and we divide it by 6, which is the number of operations, we see that actually what we get is something around 2, right? Which is, it's a constant 2. So it's basically what you can say is O of 1, right? Because that's, and then you can see that it works for basically any argument. So like if you say that the internal size is now 10 after that, you would say, okay, fine. Now we do another, few insertions, 1, 2, 3, 4, 5, and then finally you have to do another operation where you double the size, but you see that you had to do about n over 2 operations before you could do an O of n operation. So that's kind of how binomial heaps, or I should say Fibonacci heaps, work as well. So, all right. So let's insert some more stuff. So 5. Oh, I shouldn't do that, should I? Let's see, 13, 15, 18, 17, 12, 13 again, 14 again, and 21. So now what is going to happen if we remove the smallest element? So let's remove the smallest element. Let us skip back. So now let's remove the smallest element again. And what we see is that this is going to be something that's very similar to the binomial heap algorithm, right? Because here what we're going to do is we have a B0, a B1, or B2, and then we have a whole bunch of B0s. So what we're going to do is that we're going to start merging them like this, and then I'm going to merge these two like that. And then we see that we have a B1, so now we have to merge it, so we get a B2. Okay. And so then we see, okay, there's another B0. And now we have to merge it with this B0, we get another B1. Right, so here's the B1 that we get. And then we say, okay, cool. And then we say, here is a B0, we're going to merge it with this other B0, and finally we're going to get a B1. But there's already something in the 1 slot. So keep in mind that these ones here haven't even been looked at yet. So the Fibonacci heap doesn't know that there's actually another B2 waiting to be merged yet. It just knows that it's just trying to merge all the nodes. So now it says, okay, here's something in the B2 slot. Here's the next element. So the next element's going to try to go into the B2 slot, but there's already something there. So now it's going to merge, and it's going to go into the B3 slot. All right, so actually this is a great example because now we see that there's no more merging to be done. All we have to do is scan through the rest of the elements, and we would say, next element is 12, it goes into the B0 slot, or, okay, next element is this goes into the B2 slot. This next element is 71, it goes into the B1 slot. And next element is 12, it goes into the B0 slot. Okay, and that's it, really. So that's basically how this works. And so basically the Fibonacci heap is a binomial heap that's just a little bit lazy. It just waits until it basically waits until remove min to do the binomial heap operation, right? And so basically the way to imagine this is that it's kind of like if you waited to do the addition. So you know that a binomial heap is like an addition operation of two binary numbers. So it's basically like if you added, so like what should I say? I should say that a binomial heap is the addition of two binary numbers, really. And so it's something like 1, 0, 0 like that, plus something like, 0, 1, 1, 3, 0, 1, 0, 0, whatever, right? As long as there's a bunch of zeros and ones, we're happy. And then when you add these two numbers together, I guess you're going to get 0 carry the 1, 0, so then you're going to 1, and then 2 zeros, and then there you're going to get a 0 carry the 1, another 0 carry the 1, another 0 carry the 1, and then finally you get 1, 1, 1. I think this is what you get when you add them. I could be mistaken. Let's just double check for a second. 1 plus 1 is 0, carry the 1. 1 plus 1 is 0, carry the 1. There's a 1, 0, 0. 1 plus 1 is 0, carry the 1. 1 plus 1 plus the extra 1 is 1, carry the 1. 1, carry the 1. And then here, this is the carried 1. This is, oh, we don't need that. We don't need to carry in the last digit. So anyway, this is like the binomial heap. But a Fibonacci heap is kind of the same thing. except it waits to do addition operation. So basically what it does is it just queues up, like every time you do an insertion, it just queues up a whole bunch of ones like this, and then whatever you have left over from the previous stuff. So it's possible that then you'll have something like this, right? And so let me just space this over so that it's correct. There we go. So these are all the insertion operations that just give you an extra B0, which is just one node. So this is kind of like the arithmetic operation that a Fibonacci heap asks you to do. And then in the very end, you get to add all of this. But of course, you'd be like, well, how do I add all of these carries? The answer is you basically, at least the way that the visualization is doing it, it's adding these. Basically what it's doing is it's saying, add these, okay, cool. Right? Actually, I'll just do it in a separate thing so that it's more visible. So it's like adding these two, and then it's saying, okay, now we have this one. Then it's adding these two, and then it's saying, okay, we have another one, so add it and carry the one. Okay, we have another one, so stick it in. And then here's another one, so now we have to add it here, so this will be 0, carry the 1, and then we have a carried 1 here, so this will be 0, carry the 1. So this is like what the remove min operation does. Right? It just kind of goes and it adds all those 1s all the way down until finally you just add it to the big number and then merge it all together again. So that's basically binomial heaps. There's one last thing that I should talk about just a little bit, and I'm just going to pull down the, I'm going to pull down these lecture slides to talk about it, just so that I can discuss exactly what's going on. So these I think are, I know that I'm stealing these from Princeton, but I'm pretty sure that Princeton stole these from the algorithms book. So I think they stole them from Corman. I could be wrong. Let's check. I think we can find these diagrams in Corman. Fibonacci heaps. Let's see if we can find these exact diagrams in Corman. Almost. Let's see. Nope. Maybe they made them their new. Maybe they made new ones. Okay, I lied. I swore that they just stole these from Corman because I was like, they look like the Corman diagrams. Basically, these are the Corman diagrams here, but the Corman diagrams draw in all these extra dashes and stuff, and they actually store these as linked lists in the this is basically from the algorithms book. They store all of these things as linked lists. Whereas you know that you can just store them as a vector. You don't have to store them as a linked list. Now, you can if you want. Again, it's totally up to you. You see that they're storing it as a doubly linked list. Okay, if you must, right? It's not a big deal one way or the other. So anyway, okay. Let's talk about let's see, marking nodes. Where do they start talking about marking nodes? Okay. So note here that some of these nodes are gray and some of these nodes are black. And so there's an extra operation that they implement. Do you have a pointer to min? Yes. So yeah, let's just look at this, and you notice that there's some nodes that are marked and some nodes that are unmarked. And you notice here that there's this B, I guess you would call it like a B3 or something, but it's not right, if you know what I mean. Because here, it has 3 children, but it's not, the children aren't full. So how did that happen, right? The answer is that there's an extra operation on the Fibonacci heap that you can implement called decrease key. So let's talk about decrease key. So not delete min. So delete min is exactly what I said it was, right? Delete min will consolidate all of these, and here you see what it's doing. Let's actually just go through the delete min that they're doing here. Okay, so deleting minimum here. Here's their starting position. So 3 is the minimum, and you see, yes, you do have a pointer to it. And then what you do here is you delete the minimum, and then you see that you're going to end up with like a B0 and 2 B1s that you're going to have to merge in. I guess there's also a B2, and there's a B1, and then there's 2 more B0s sitting around. And I know I'm calling them B0s. Technically, they're all just called trees of rank 0, trees of rank 1, trees of rank 2. I'm abusing the notation. And so we do the same thing that we do for the regular binomial heap. We pull off the node, and then we stick its children onto the root list. That's generally what this was called, is like the root list. And then we have to do our consolidate operation, which I'm calling merge. I don't care if you call it merge or consolidate or whatever. So, okay, how are they going to do this? The real question, so this operation depends on how they read them, right? So if the min is here, let's see what they're about to do. So that's equal to the current, and so then this will be so this will go into the B1 slot, this will go into the B2 slot, this should go into the B0 slot, and then we should start getting some merge operations as soon as that happens. So let's see what happens here. So this goes into the B1 slot, now that they have these slots, the rank slots. So this goes into rank 1. This goes into rank 2. This goes into rank 0. And this is as much as you can do, right? Because now you see that we have 2 more rank 0s, we have 2 more rank 1s, so there's going to have to be some kind of addition going on. We can't just stop here. So, okay, let's try it now. So we see, okay, what happened? So here's the current. Nothing's happened so far. But the current sees that there's something already in the 0 slot, so it says, I can't add myself there. I got to add it. I got to merge these 2 nodes and then do the operation. So let's see. There we go. So now the current is equal to this B1 rank 1 thing. Let's see. Right. Okay, yes. And so here what they're going to do is they're going to merge this 17 with this 7 because it's already in the rank 1 slot. So let's watch them do that. So now they're merging it. And again, you know, you could do this in a lot of different ways. So there's not like one predetermined algorithm for this. That's the problem. That's why I had to kind of cheat and look ahead, is because you see, oh, there's another B1 here. Why didn't they merge it this way? I don't know. No particular reason, right? That's the thing, is that the only reason why they merged these 2 is because I guess they knew that they had something in the rank 1 slot already, and so they got to merge it. So here we merge the 2 things in the rank 1 slot. Now we have something in the rank 2 slot, so then we're going to create this big thing with the min pointing here, the current pointing here. We're going to merge this on and make a B3, an honest to God B3, and stick it in the 3rd slot. And then we just have to deal with the remainder crap. So here's a rank 1 thing, a rank 0 thing, and a rank 1 thing. So basically you know that the rank 1 thing is going to go here, the rank 0 thing is going to go here. So rank 1 thing, rank 0 thing, and then finally there's one little thing left, which is going to be this other rank 1 thing, so then we will do, right? Well, almost. So now they're like, here's the current. So you know that this is going to have to merge. So it's going to have to merge with 18. And so when it merges with 18, it's going to go down. And it's going to go down right here. And it's going to become a B2. And it's going to get moved from the 1 to the 2 slot. There it is. It merged with the 41. And finally, it gets stuck in there. And so now what we know, and so basically at this point, we know we're done because we have this vector of ranks. And we know there's nothing left to be searched in our root list. And so because there's nothing left to be searched in our root list, and everything is only in 1 rank slot, we know that we're finished. So that's how to do it. Okay, let's see. What else? Okay, nothing else, right? STOP. So consolidated trees have no blah, blah, blah. Let's see. Consolidated trees, so now no two roots have the same rank. Yes, right? That's the whole point. And when you say consolidate trees so that no two roots have the same rank, that's the exact same thing as saying you merge the two trees, or you merge all the trees until until there's no duplicate BIs, right? And you see here that this thing, I mean, it's not quite the same data structure, but you see that in reality, other than the marked nodes, it is really just a Fibonacci, not a Fibonacci, it's really just a binomial heap, because you have a B0, you have literally a B2, and you have a B3. Done. I mean, this thing could actually be a binomial heap. So, okay. Let us look at the decrease key operation. And I'm not going to talk too much about it, but I do want to discuss it because it's the decrease key operation is the thing that makes a Fibonacci heap different than a binomial heap. It's the thing that makes it so that you don't just get BIs. So if you don't implement the decrease key operation, you definitely don't need a Fibonacci heap because it's going to be the exact same thing. Is this my favorite heap? I kind of like it. I kind of like binomial heaps the best just because they have a lot of nice mathematical properties. This thing can tend to... I think I've implemented a Fibonacci heap once. It's really awful. I wonder if we could almost make my binomial heap into a Fibonacci heap. So, but let's talk about decrease key, okay? So sometimes, let's say that what you want to do is you want to take a key and you want to decrease that key, right? So what can happen if you decrease a key? So if we make this value, let's say that we make this value, instead of 52, we make it 20, right? Then we see what the problem is here. The problem here is that if it's under a 21, then we can't actually do that, or I shouldn't say we can't do that, we can do that, but the problem is that it violates the heap property, right? Every node here has to be smaller than its children, because this is a min heap. You could make a max heap version of the same thing, but who cares? This is the min heap version. Just a reminder, your project is a min heap, by the way. So what happens here if you decrease this key to 20 and you say, well, I don't know what happens. It violates the heap property. So how does a Fibonacci heap tell me how to fix that, right? So let's see how we're told to fix it. So I will show you. So here, let's see, decrease key of X. So let's see. Okay, so this was 46 back here. So they're going to decrease it to 29 here. So what you see here is what? Nothing, right? So here, this basically says decrease the key from 46 to 29, and you would say to yourself, okay, cool, right? It doesn't violate the heap property, so you don't do anything. You leave it as is, all right? So let's see here. Okay. So this is the other case, right? This is the interesting case. So what if it does violate the heap property? Well, then we have to do this operation, but I'm just going to show you the operation at work. I'm not going to read through it yet. So what you're going to have to do is you cut the tree rooted at X, meld it to the list, and unmark it. And so here you see that 15 is not marked. 26, 18, and 39 are marked. So that's what it means by being marked, is if they're like doubled, if they have this extra notation on them. But 15 isn't marked. It violates the heap property. So guess what you get to do? You get to basically prune this piece of the tree off, and you stick it onto the root list. So now what you're going to get is you're going to get 15 and 72 here, and that's what you get. Or, okay, fine, they put it over here, 15 and 72. As you see, it doesn't really, again, it doesn't really matter where you stick it on, okay? So that's that, and then you're done, right? This is done. Okay? Okay, so then if the parent of P, or, well, I should say this cutting operation is done. So now we have to do this. If parent of P of X is unmarked, mark it. Okay? So now 24 was the parent, so it's going to get a black circle. All right. Now we're done, right? So if it's unmarked, you mark it, and then you're done. Okay, but what if the parent was already marked? So let's see what happens if the parent is already marked. So let's decrease this key now to 5. Basically, the way to think about the decrease key operation is like, imagine that you're, let's imagine that you're doing a real patient triage heap. For some reason, right, you were a robot hospital and you had to do a triage thing like you do in your project, except that you actually want to reevaluate the patients, right? And what if one patient is sitting there in the emergency room and you think, oh, that patient is fine, like all their vitals are fine, everything about them is fine, they're a low priority, right? They get a high triage rating. But then, let's say that they collapse on the floor and they're having a heart attack. Well, then that's the decrease key operation. That's basically saying that patient has just, it turns out that they're sitting there calmly, but actually they have a spike through their hand or something, and you're like, oh, well, that's a problem. So what you do is you decrease their key to increase their priority, right? And that's what this operation is doing. Basically, it's saying, oops, we misclassified this node, this person, whatever, had a much higher priority or a much lower value in the case of a min heap than we expected, and so we want to modify that so that then they can get help faster, right? We want to push them up in the queue. It's like, if everybody's in line in a grocery store, but then someone's like, oh my god, I just forgot, I have a plane to catch in 10 minutes or in an hour or whatever, and so everybody's like, okay, I guess you can check out first, right? That's what decreased key operation does. Or I guess it's like the little old lady phenomenon. They get in the back of the line, they accept that their key is low, or I should say their key is actually very high, and then everybody looks back and sees them and it's like, oh, it's some old 90-year-old lady, so guess what we're going to do? We're going to decrease her key so that she can go up to the front of the line. So that's what this operation is doing, right? So decreasing from 35 to 5, what that's basically saying is that this is grandma, right? And she needs to get to the front of the line. So the rule here is that if the parent was marked, right, then what we do is we cut it as well. So we're going to cut 5 off and we're going to stick it into the root list. So we're going to cut 5 off and stick it in the root list. There we go. Cool. But now we're going to have to do an extra operation because the parent was already marked. If the parent was already marked, then we cut it off and we stick it in the root list. And the reason why we do this is because what the marking means, remember what marking means. What marking means is that you've already had a child who's been reallocated up to the root list, right? So it means that you're kind of a person who's already been bypassed once. And so the rule in the Fibonacci heap is that you only are allowed to bypass, little old ladies are only allowed to bypass you once. If there's 20 little old ladies in line, then what happens is that once the first one passes you, you get to put yourself up because you get like a I got passed mark once. And so if you get passed once, then you get marked, and so then you're special. So then the next time that this happens, you get to also follow the little old lady up to the root line and be in like another checkout line or whatever you want to call in this analogy. So basically here you see that the root was the parent was already marked, which means that the parent had already been bypassed at some point in the past. And so what you do then is then you recursively, as it says, you recursively head up towards the root of this tree, and you basically cut every marked node, right? Cut every marked node and merge it back in. So let's watch that happen. Here we go. We're going to cut you off, right? And stick you into the root list. Because even though you're 26 and the granny was 5, you definitely you got passed already once, so you get to go up to the front of the line. And actually, the cool thing about that is that you get to bring all of your surviving children with you. So anyone else who's behind you gets to kind of benefit from the fact that you were marked. You're at 88 wasn't marked, but 88 was 88 follows you. So, and then here, so remember that we have to do this recursively, so we can't just stop here. This is the parent of the thing that was marked. So here's P prime, as they're calling it. There we go. And so 24 gets cut off. If 24 had any extra children, it would bring its children up with it, but it doesn't because it doesn't have them. There we go. So now P prime is also with the root list. And here's a special case. It really doesn't matter. So don't mark the parent if it's a root. Now, why would you say that, right? Don't mark the parent if it's a root. So you could also mark the parent, right? Because the child just got removed and stuck into the root list. But the parent itself is in the root list already. And what's the whole point of marking, right? The whole point of marking is that if you get passed again, then you get to go into the root list, but you're already in the root list. So that's why this whole don't mark the parent if it's a root, it doesn't really matter, right? Because, well, I guess it kind of matters later on, but you know what? At least in this operation, it doesn't really matter, because if you mark this guy, if you mark 7, 7's like, hey, I'm already in the root list. It doesn't matter, right? Don't matter. On the other hand, if you don't mark him, then he's like, okay, I'm already in the root list. It really doesn't matter. So that's kind of the point, is that all of these people are the first up for consideration because they're in the root list, and all these people here are waiting behind other people who are waiting in the root list. So that's kind of the idea here. So that's why decrease key works the way it does. So remember, there's 2 cases in decrease key. The 2 cases in decrease key are 1. Actually, I guess there's 3, right? There's like 2A, 2B, but there's really 1 case. Here it is. Decrease the key of X. Well, if there's nothing, if you don't do any cuts because this thing is in heap order, right? You do nothing. Right? You decrease the key. And do you even mark the parent? Do you do that? I think you don't, right? But now here's case 2A, right? So instead of being 29, now it's 15. So if it's 15, that this does violate heap order. So remember what you do here. This is the easier case. You cut this, and then you cut this, and you mark 24, because 24 is unmarked. Right? The parent is still 24, but 15 got removed, and then 24 gets marked. So that's the case 2A, right? Heap order violated. But then we're done, right? Because we found an unmarked node, so we don't have to mark it. Or I'm sorry, we found an unmarked node, so we mark it, but we don't have to cut it. All right, so now case 2B, right? We decrease this key to 5. So we know that we cut because it's violating heap order. There we go. Oh, no, it hasn't cut yet. There it goes. Now it's cut. Its parent is marked, because and remember what just marked means. Marked means you've already been passed at some point. So if you've already been passed, you get a free pass to the front of the line, or at least to the top of the Fibonacci heap. So so then this one gets cut and stuck on here, and then you unmark it. Now you only unmark it. Remember why you unmark it. So the reason why you unmark it is because it's the I've been passed mark, and it means that I get a free pass to the top of the line. But if I'm already at the top of the line, then I don't get another free pass to the top of the line. I'm already at the top of the line. So that's why you unmark. And then here you would say that P prime is 24. Remember, because 26 was the child here. And so basically 24 is also marked, so it gets cut and put into the root list. Yes. So, and then here's double prime. So don't mark it if it's the root, because guess what? It's already got a free pass to the front of the line. So now you see, if you had something like this, right? If you had something like this and you did another like insertion operation, you would just add it to the root list. But if you did a remove min operation, you would kill off this node, and then you would have a whole bunch of stuff to merge, right? Basically, if you merge all this stuff, let's think about what this is. If you merged all this stuff, what would this be? This is really a... Let's think about it. So this is really, and let me start from this side. This is a 1, 0 plus a 0, 1, but that gets removed, plus another 1, 0, plus another 0, 1, plus a 1, 0, 0. So now we have to add some spaces to make all of that work. Plus another 1, 0, 0, right? Because this is a... and then finally plus another 0, 1, 0, right? So when you add all of this together, if you did another remove min operation, what would you get? You would get in the end 1, 1, but then we have to carry a 1, and then 1 carry another 1, so you get that. I think you have to check my arithmetic, but otherwise I think that's right, right? Because there's only one thing in this slot, so here you get this. You have 1, 2, 3 things in the 1 slot, so you get, 3 is equal to 1 carry a 1, and this is now equal to 3, so that's 1 carry a 1. So I think that's how the addition should work for the next remove min operation. So anyway, that's why that is the, let's see, yes, so that is how this works. Okay. So, does anyone want to implement this thing? For extra credit. This thing is, I'm not gonna lie. This thing is kind of a, it's a gimmick, right? It's kind of a, it's a gimmick. But, so the question is why did such a thing exist, or why does such a thing exist? And so they show you here, let's see here. Basically, their argument here is that the rank of h, on average, is less than or equal to the log base phi, which is the golden ratio of n. And so if that's true, then the amortized time is going to be O of log n for delete. So this whole thing was literally invented to get a better, I think it was in Dijkstra's algorithm. Am I right about that? I think in Dijkstra's algorithm, if you implement, so Dijkstra's algorithm uses a heap, and what it does is it takes out the minimum edge every time, and it kind of adds it onto your graph. So, and basically it's trying to find the minimum path through a graph. So, and what it does is it uses a min heap to do so. So, here's the famous thing. Fredman and Tarjan in 1984 proposed using a Fibonacci heap to optimize the runtime to O of E plus V log V. And so it optimizes it better. It's better than O of V plus E log V. So, or theta of V plus E log V. So this is like the famous, it's so famous that it's in fact part of the Dijkstra's algorithm, like, prelude here, or whatever you would call this, the introduction on Wikipedia, right? So this is like the entire point. We will talk about Dijkstra's algorithm in the future. Yeah. So basically, that is the Fibonacci heap. Okay? So it's pretty fun. It's kind of I admit it's a bit of a gimmick. For practical applications, it's better to use leftist heaps, binomial heaps, regular array heaps. Most applications in your life, this is not the right answer. Like, you need to be operating on a graph of like 10 billion nodes, right? And using Dijkstra's algorithm. And then you're like, I remember. That's when we use a Fibonacci heap, right? So you have to be remember that big O only makes sense for operations of sufficiently high n sometimes, and here, like, mostly the array heaps and the leftist heaps and skew heaps and binomial heaps, they perform well enough to where you don't have to worry about this. On the other hand, this does complete our heap excursion, okay? So this completes, for the most part, our traversal through heaps, which I think is kind of it's happy, but it's sad, right? We experienced a lot of different heaps. We loved them, we hated them, we implemented them, and that's it. So I won't bore you to death with an implementation of a Fibonacci heap. I mean, we could try to do it in 10 minutes. But I won't even bore you with that. I mean, I don't think I'd be able to finish it in 10 to 15 minutes anyway. Very unlikely that I'd be able to do that. So, I don't know. Other than that, I guess we could talk a little bit about the runtimes and let's just do one final sum up of the runtimes. So the runtime for insert on a binomial or on a Fibonacci heap is O of 1. For remove min, that is O of log n amortized. Right? Sometimes it's going to be O of n, but we expect that to happen. But that should happen rarely. So remove min. What else? And then the other one is just decrease key. Right? So decrease key is also going to be O of log n. And so that one is going to be O of log n as long as you know where the node is. So as long as you have a pointer to the node. The thing that they never talk about is that if you don't have a pointer, you have to find. And remember that find in any heap, right? If I just said find some particular node, that's always O of n, right? Because you might have to scan through every single place to find a particular node. Heaps are not great for finding nodes. But this is for Fibonacci heap. So the difference between it and a binomial heap is that the binomial heap insert is actually O of log n. Remove min is also O of log n. And decrease key doesn't exist. I mean, we could make a decrease key that did some swapping operation or something like that. Yeah, we could make a decrease key. But this one would involve a swapping operation. And this would also be O of log n. So basically, binomial heaps are good if you want. None of this is amortized. This is all guaranteed 100% log n runtime. This one, the secret is that if you expect a lot of insertions, right? this one is definitely better because you get a lot of O of 1 insertions, and then you just get a single log n operation for the remove min. And so that's way better than doing a bunch of log n operations, right? If you insert like 15 elements, or insert like n elements, then that should take n log n time, right? Which is worse than the Fibonacci heap, which would just be n time for n insertions. So that's kind of the benefit. And you might be like, well, but I don't really care about this extra log n factor in most cases in real life. Like, the log n factor is almost for free. Sometimes the log n factor with sizes of nodes, like if the number of nodes is less than 1 million, then if your actual constant C in front of big O is bigger than 5 or 6, right, then the log n factor actually disappears into the constant. So it really doesn't matter. But on the other hand, I mean, if you're doing a lot of insertions, maybe a Fibonacci heap is a better thing. If you're doing a lot of decreased keys, remember that the rules for marked nodes are basically as you go up, if the parent isn't marked, you mark. If it is, you cut and join it to the root list. And you do this recursively. So basically, I should say until you find a root or an unmarked node, which you then mark. So that's that. That's Fibonacci heaps. Okay? Yeah. So I think I'll end class now. I didn't discuss... what didn't I discuss? Hash tables. But guess what? That's maybe next time, next Tuesday. So next Tuesday, what I'm going to do is I'll probably go over the project and teach hash tables at the same time. Yeah, so this is n log n for n insertions, right? So if I insert n objects into a Fibonacci heap, or yeah, into a binomial heap, if I insert n times, then that should be an O of n log n operation, right? Because each insertion is O of log n. And then here, if I insert n insertions into the Fibonacci heap, that's n times 1, so that should be O of n, right, for n insertions. So anyway, yes, so what I didn't discuss was hash tables. We'll go over that next Tuesday. We'll do that, and once the project, I think the project will be released next Tuesday. So the good news is the project is on hash tables. We are about to cover hash tables. Hash tables are relatively easy objects, so I am not terribly afraid of covering them on the first day of the project. If there's anything really complicated about it, then maybe I'll do some extra lectures about the project and about hash tables. But hash tables are going to be like 2 days anyway. My anticipation is that we're going to... Hash tables are... basically, the gist of hash tables is that they're souped up arrays. They're arrays that allow you to insert objects that have hashed key values. And I'll show you all that next time. Let's not even talk about it. Okay? Once I see the project, I'll know how to direct the lecture. And so that's what we'll do. A hashable tree of tree. Let's hope not. Okay. Actually, I think the one thing to say maybe, if you remember what a Python dictionary is, that's a hash table. So that's how I'll end the lecture. I'll just say that a Python dictionary is in fact a hash table. It's just called a dictionary in Python. In Ruby, it's called hash, so it's actually correct, like called the right thing. Other languages can have certain things, like Java, I think, calls it a hash map instead of a hash table. Who cares, right? Basically, every language has its own word for it, but I generally call them hash tables. In fact, on Twitter, when you hear the term hashtag, that's actually referring to hash tables. Because the hashtag is itself hashed and put into a table. And that's how it works. So basically, if you have an idea of how to use a Python dictionary, then you know how to use a hash table already. We just have to talk about the internal mechanism and how the operations work. But otherwise, it's really, don't worry about it, right? Just worry about heaps. Just finish your heap project. I'll be available somewhat over the weekend if you need any help with the project. I hope most of you are done. Hopefully most of you who are watching the lecture are completely done because you're just so confident and absolutely, A+ done with the project. All right. I think that's it. So let's run the outro and say goodbye. I've talked on for long enough.